All right, go ahead.
Okay, well, thank you very much for the introduction. So it's a pleasure to have this opportunity to give this talk on surrogate modeling for stochastic simulator. So just a few details on my group. So I hold the chair of risk, safety, and uncertainty quantification at ETH. And we basically work in all aspects of uncertainty quantification, originally for engineering problems, but more and more for many other problems, from economics to astrophysics to many more. Well, with application, as it was said, on surrogate models, reliability, sensitivity analysis, model calibration, Bayesian techniques, and so on and so forth. And today, I will about surrogate modeling more specifically, and for these so-called stochastic simulators that I will explain in a minute. So this work I will present here is carried out within a project funded by the Swiss National Science Foundation for about 3 years now, which allowed me to have 2 PhD students and a postdoc on this topic. And what I will present today is mostly related to the first PhD, Shuja Zhu, who developed techniques for surrogate, for stochastic emulators, as we call them, using Lambda distribution. So that will be the main topic of this talk. So as you know, we do more and more computational models to basically design or assess systems, the engineering systems in my case, but also, let's say, natural system, biological system, whatever. And the tradition is typically that we have some governing equations, some mathematical description of the phenomena, which are usually differential equations in most cases, and you don't have a closed form solution for applied problems. So what we do is that we discretize these equations in space and time, and we transform them problems that are then solved, discrete problems that you solve with techniques from linear algebra, especially because computers are very good at solving this kind of discretized problems. And so these computational models, basically we use for various purposes. In my field, well, basically there is a step where you should calibrate your model. So that's the last point here in this list, but typically you want to validate the model, that is, make sure it's predictive with respect to the phenomenon you are interested in. And so this is usually carried out with comparing experiments, real physical experiments with predictions. But once you have this done, so you're confident that the predictions are okay, then what is good with this computational model is that you can vary parameters and see what happens. So basically you devise this way what we call virtual prototypes. So instead of testing various solutions and really prototyping and testing them, basically you do these simulations of the behavior of different systems, varying, let's say, the dimensions, the materials, or even the load cases, and then you compute certain performance indicator and solve somehow the problems directly in silico with the computer model. We can go one step further, especially when, well, let's say the underlying physics is well established. For instance, for, let's say, structural mechanics, fluid mechanics, or electromagnetism, the models nowadays are very, very good. So we can put our computational model into an optimization loop. And typically the goal there is to minimize the cost or the mass of a system under certain performance constraints. And now when we talk about, well, the let's say, in silico model of the system, or the design one versus the system in real world, there are always sources of uncertainty, discrepancies, variability in the, let's say, usage conditions, or also in the materials, or many other possible parameters. So if we want to take this also into account, then we have to model those uncertainties, and then we are able to somehow evaluate and quantify the robustness and the reliability of the system, which again is better than doing a huge campaign of experiments to assess these quantities. So that's just a short introduction. Now, from a more abstract point of view, what I would call a computational model in this talk is basically this black box that maps the input parameters of the problem that usually describes the system and vary in a certain range to these quantities of interest, this performance indicator in practice that you compute to be able to, that you want to use to assess or optimize your system. So again, coming from computational mechanics, typically in our such models, you describe the geometry, the material properties and constitutive laws of your system and the loading, and what you want to compute is typically displacement fields, velocity fields, strain, stresses, temperature, chemical quantities, whatever. And as you see in the middle here, by the way, my mouse here moving around. Yeah.
Yes, we can see it.
Yeah, okay, so I can use it then. So as you see here, what I call the model is really a black box. It can be very simple. It can be just simple analytical equations up to discretized partial differential equations, for instance, finite elements or finite volumes, up to complex computational workflows that do a series of analyses. Now, in most problems we have in engineering, we have so-called deterministic models or simulators. What does it mean? It means that really this mapping from input parameters to an output quantity of interest y is really just a function in the usual sense. That is, if you take a value of x, you run your model, you get the corresponding y, and that's it. So if you repeat the analysis with the exact same x, then you get the exact same y. So it's really a deterministic map function from x to y. What is our topic today is what we call stochastic simulators. And this is as follows. You have here again a certain number of parameters that will typically vary in a range or in input space, but there is also inside the simulator other sources of stochasticity. So in the sense that now if I take x equal 1 and repeat different runs of the same simulator with this x equal 1, I will get all along different values, and in the end this is characterized by a distribution. So in other words, for a given x now, the output is not a real number or vector, it's now a random variable that we would like to characterize. So why are we interested in this? Because as I said, it's less common than our usual tools, but it occurs, these stochastic simulators, in many different fields. From engineering to start with is the wind turbine simulation. So here you see to the right a typical wind turbine, maybe it's offshore here, and to design and assess the tower, the blade, and everything, basically you do simulation with something called aeroservoelastic simulator, from which one input is basically a wind field. So really, in this plane here in front of the blades, you have typically a 10-minute movie of a field, a velocity field of wind that is related to certain characteristic. And this is obtained from a wind generator, which itself depends on a few parameters. So typically here you see the main parameters that would be the mean speed in front or in the direction orthogonal to the wind turbine plane, the turbulence intensity here, which is shown here with this curve, and what is called shear exponent is basically the curve describing the dependency with the altitude here, plus possibly two other parameters. But basically there are just a few parameters here, and a wind condition or wind climate will be given by just these 5 values. Of course, then we study many different scenarios. But given these 5 values, then the wind generator is able to provide as many wind fields of 10 minutes as you want, because there inside there is some simulation of Gaussian random processes. So when you put those wind fields onto the wind turbine, and finally maybe you are interested in some mechanical properties, mechanical output here, the bending moment in the blades or certain stresses, what you get is basically, for a given set of input parameters, a full distribution of those output quantities, because they all correspond to different realization of the wind field, although the input parameters are set once and for all. Another example you're very familiar with probably is in epidemiology, in these SER models, where basically you have a population, you have, in the simplest case, just 3 states, susceptible individuals, infected and recovered, and some transition between the different categories. And this occurs, let's say, at each time step with a certain probability. So you can have a certain probability that a person gets infected, which is not one-to-one. And then within this model, you have a number of parameters, which are these famous rates of different kinds. So here again, if you consider deterministic values for the, let's say, original input, original situation, and also of the factors that describe the different transitions, there is inside the simulation some random processes that lead to typically a random population that is infected at a given time instance in the future. Final example is related to mathematical finance. So here I'm less an expert on this, but you probably have seen already this kind of so-called stochastic differential equations that are very used to model typically stock prices or derivative products. And here, basically, you have, again, parameters in differential equations, but you have also a source of stochasticity with a ground motion here. So in that case, again, if you fix what I call the parameter, that would be here in this equation, mu and sigma, and you repeat analysis, you will have different trajectories and get different results after, let's say, a year. So this is the motivation to, better understand how this stochastic simulator works, and basically being able to do some kind of surrogate models for applications where just a brute force Monte Carlo simulation of those conditions and stochastic simulations would be not feasible. So the outline of the presentation is as follows. I will give some literature hints in the first part here. Then I will talk about this general Lambda distribution that I will use, and present then our approach, which combines this Lambda distribution and polynomial chaos expansions, and finally show some applications. So formally now we can define what is a stochastic simulator as opposed to this deterministic one, which was just a mapping from X to Y. Here it's now a mapping from a product space of input parameter X and then a probability space, which I denote here omega, the random events. And here what you get M of X and omega is a variable. So meaning that if you fix a particular X to X0, what you get is that particular conditional random variable output condition on X equal X0. And in contrast, if you were to fix omega, so in practice in these stochastic simulators, of course, in the computer, usually nothing is random. It's just that you have some hidden parameters that are drawn randomly, but you can still manage this with so-called fixing the seed of the random number generator. So if we do this here, we taking a particular omega 0 and varying the X, what we get is basically what we call the trajectory here of this simulator. One way to represent this in practice is to consider that the stochastic simulator is actually a fully deterministic function of two types of parameters, the x's that you explicitly mention as input parameters, and then the hidden variables that are all those randomly sampled variables into the algorithms that I represent here with Gaussian variables. So it's very common that here it's a huge number of standard normal variables if you simulate random process, or it could be variables related to a Poisson process, for instance, in certain applications. Now, how to handle? So the question is really how to represent the distribution of y for a given x. the natural idea is that, well, you take this particular X and then you run again and again the code. So that is what we call replications. And then if you do many replications, it's like Monte Carlo. So you basically get a large number of samples of Y given X, and then you have the distribution. The thing is that now if X itself has to be varied because you want to do uncertainty propagation on the X's, or you want to do sensitivity analysis, or possibly also optimization, then you see that you have to do many runs of this basic computation. And each single run, if I take the wind turbine example, is typically half an hour or could be even more. So it's extremely costly. So this is why in practice, if we want to be able to use more and more of this type of modeling, we need also surrogate models for stochastic simulators. What is a surrogate model? Well, probably most of you know already. Let me come back for a second to deterministic simulators. In that case, what we call a surrogate model is just an approximation. So remember, this MD for deterministic here is a mapping from X to certain output. Here we want to find an approximation, so an approximate function, such that this equality or approximation holds in certain sense. And the idea is that each run of MD of X may be very costly, but if we assume certain additional assumptions, typically some regularity assumption on M, and we use a limited number of runs of this true model MD for selected points in the input space that we call the experimental design, based on this, we will be able to build this M-tiled function. And then, of course, the M-tiled is such that it's very fast to evaluate. So typically here, what are nowadays well-known surrogate models for uncertainty quantification, but also for optimization. It's been used in really many different fields. There are polynomial chaos expansions, where here this ansatz that we take, so this representation, is just a sum of coefficients multiplied by certain particular orthogonal polynomials. So the parameters of such a model here are these coefficients, and that's exactly what you want to compute from the data that is collected here. There are other well-known approaches like Gaussian processes, support-vector machines, and of course, in a sense, neural networks also belong to this kind of surrogate models, except that usually neural networks are used directly with whatever data that is gathered, and not necessarily in the field of computational or scientific computing, or even less in the field of uncertainty quantification. But in principle, that's the same. In our case here, to build surrogate models, so as I said, we will choose an experimental design, so limited number of points in the input parameter X, typically using Latin A/cube sampling, and then we will run those original model for those points, but it's now a limited number of runs. And then we use this input-output set of data through an appropriate learning algorithms to fit the coefficients of the surrogate model that has been selected. So the coefficients in the PC expansion case, typically with least square solutions, or the parameters of the trend and of the correlation function for Gaussian processes. Very important in any case is that we validate the accuracy of the surrogates and typically get some estimation of this generalization error, typically the mean square error between the original true model and its surrogate. So that's just really in few words for deterministic models and surrogates. Now we want to do the same, more or less, for stochastic simulators. So we want, again, something that is non-intrusive. We don't want something that would work only for a specific type of equation, which is implemented in the simulator. We want it to be general purpose and specifically not assume a priori that the distribution of the output is Gaussian, which is what many people do. we want to be able to represent this full conditional distribution, but albeit also to be accurate in certain quantities of interest. For instance, for wind turbine design, that will be upper quantiles in that conditional distribution. And we want to be able to resample. So how to start with? There are many approaches already in the literature. There are, I will just give a few hints on those ones. So replication-based Gaussian models, conditional distribution models, latent variables, and random field representations. So the replication-based approaches, that's possibly the most natural way. If you want to characterize the distribution of y given a particular x, so you fix this x, you repeat the calculations, you get those samples, and you try to characterize this distribution. But you cannot do this for all possible x's, so you would do this for typically a number of points as shown here, and then the parameters of this distribution, if you consider a parametric family that is the same all along, then you can represent those estimated parameters as a function of x. And these parameters, typically, if you were to assume here, I don't know, Gaussian distribution, you would have two parameters depending on x. So then you have two deterministic functions to surrogate. And this is what is done in this stochastic kriging approach, quantile kriging approaches, also with this kernel density estimation here. And this was our starting point, where we basically tried to start approaching the problem this way, but in a more general ways, thus this introduction of lambda distribution. There are many approaches that basically are based on kriging and somehow are based on the fact that the output distribution for a given x is just Gaussian. So in that case, it's kind of simplifying the problem. You just need to characterize the mean function and the variance function of this. And typically people represent mu of sigma and the log variance by Gaussian processes. So there are, well, quite early works with these ideas, but there's also a lot of recent papers in this area, especially for like adaptive design for such approaches. So there are recent papers that you can find on this ground. Another way is to consider this really as an estimation of probability density function. So in the end, the distribution of y given x is just a conditional distribution. And if we take the joint data of x and y and we are able to characterize the joint distribution, then by dividing by the marginal distribution of the x's that in practice usually we know in the context of UQ, then we get this conditional PDF. So here again, you can use parametric or non-parametric approaches. So there have been some kernel spoofing non-parametric approaches, some Vine copula, let's say, representation of these things. And this is also something that we have used recently. Another idea is to kind of introduce explicitly this latent variable. So as I said, they exist some latent variables in your stochastic simulator, but it's hidden. You don't want to show them. And the idea would be to find a surrogate function of the x's and some latent variable z times. So not the ones that are in the simulator, but in such a way that you have the same distribution. When you fix the x, you have the same distribution of this n tilde, where the variability just depends on the z tile here, and on the distribution of y given x, which is what you look for. So again, there's been recently some work in this area with also techniques from machine learning, a deep neural network, especially. And we recently worked also here with, again, what we call stochastic polynomial Gauss expansions. The last approach, so you see it's somehow very wide, the way you can address the problem. This one is very recent, so it's something that I've been collaborating to. It's to consider that this random variable for a given x, so this m of x z that I have shown already, is actually a random process, a random field indexed by the x parameters. And so, but possibly a random field with really complex properties. And the idea here is that if you fix, if you're able to fix the seed, can basically generate trajectories for given omega zeros, and then enjoy basically this knowledge on trajectories to somehow give a representation of this random field. So this is this, you see here, there's been 2 recent papers on this idea that we want to further develop with the second PhD project I have in this SAMOS project. Okay, so now let's go into the details. Well, we will use so-called lambda distribution, so I will start with defining what it is. So it's basically a parametric distribution with 4 parameters, which has this particular feature that it's defined not by CDF or PDF, but it's defined by its quantile function, that is the inverse CDF function, with this expression here. The 4 parameters have clear interpretation in this equation. Lambda 1 is a location parameter, lambda 2 is the scale, and lambda 3 and 4 are responsible for the shape and also for the support, so boundedness or unboundedness of such a distribution. If you want to get the PDF, well, you can derive it, but you see that the PDF for a given y here is basically something that depends on u, where u is the quantile associated to this y value. So somehow you have here to solve again and again this implicit equation between u and this quantity here. And this is in practice, except for a few values of the lambdas, this is something that you have to solve numerically. The point of using such distribution is that they are very versatile in the sense that by changing the 4 parameters, you can have a standard normal distribution. You can have like students, unimodal, skewed distribution, bounded or not bounded. You see the relationships here depending on the sign of lambda 3 and 4, and so on and so forth. So you can get really a full a panel of possible distribution, and that's interesting because it's still a parametric representation with 4 numbers, but if you vary them, you could cover really most situations. Only unimodal distributions, that's the main restriction, but still bounded to unbounded, skewed, not skewed, and so on and so forth. Okay, so how do we use this now? So as I said, our starting point is really to start really experimental design in the X space, and then do, as most people do, replication. So for each axis, you repeat your calculations. Of course, you need to have a random seed that is changed for each calculation, get R different values of the output. Here I take a scalar output. So what we proposed in this first paper here is a really simple 2-step approach. If you have in each point xi this set of outputs, then you fit a lambda distribution to this output, and then for this particular xi, you would get 4 lambda parameters. Now, if you do this for many different points, basically you get some kind of experimental design x1 to xn, to which you can attach the 4 parameters of the distribution, and then you basically can do whatever surrogate modeling with this input-output relationship. So that's what we did. And then there will be a second approach where we can refine this by what we call the joint inference. So let's start with the first step. As I said, you take a particular xi, you run all your models. Just for that xi, you get the output. You try to fit the lambda distribution with these points here, typically with maximum likelihood estimation. Again, because of the specific shape of the distribution, the PDF here that you put in the likelihood is not explicit, so you have to go through some numerics, but it's quite easy. And then out of this, you get for this particular xi, you get the 4 lambda i's that are associated to this. And then if you collect all the xi's and all the lambda, 4 lambda vectors that you have, then you can fit basically 4 different surrogates, but now in the classical sense. So here we use polynomial Gauss expansions. Just again, in 2 slides, if you're not very familiar, what is polynomial Gauss expansion? So it's typically done as a surrogate model or a deterministic simulator. So if you have an input random vector here with independent components and some output y equal md of x, you can represent this m of x as a series expansion based on multivariate polynomials, here multivariate orthonormal polynomials and certain coefficients. And what I mean by these polynomials is that basically to each xi here, input parameters with given distribution, you can associate a family of orthogonal polynomial with respect to this weight function, this fxi, and then you do a tensor product here to get multivariate orthonormal polynomials. So, sorry, for those of you who are not familiar, it could take an hour to explain all details, but just grasp that we have here a polynomial equation. What is nice is that if you add an infinite series, you have an equality here, but of course, in practice, we have an approximation just by truncating the series, and there are different ways of truncation. The natural way would be to, as we handle polynomials, would be to take polynomials up to a certain degree. So the total degree here is the sum of the partial degrees in each direction, in each input dimension. Basically the sum of this univariate, the degrees of the univariate polynomials in this tensor product. There are more advanced truncation schemes, especially if you have large dimensions, just to cope with the curse of dimensionality, not to have too many polynomials. And then out of this, basically, what makes this approach powerful is that we have what we call sparse solvers. So instead of solving for all polynomial coefficients selected a priori with one or the other truncation, we consider those truncated series just as a candidate basis, and then we have solvers, and there are different solvers that will just pick the non-zero term in the expansion. And this way you can handle very high dimensional problem, typically here with 50, 100 or even more input parameters with a reasonable computational cost. We use a lot least angle regression, but there are many others, and by the way, that's not the point here, but we have two recent papers on like state of the art on this sparse expansion and huge benchmarking to basically well, get some knowledge on what to do in which situation. So if you're interested, I can give you some link. Here we use basically the polynomial chaos expansion techniques really to fit the link between the parameters lambda as a function of x and the x, okay, based on these results of the fit step that I've described before. So we use this for lambda 1, 3, and 4. For lambda 2, as we have to ensure that lambda 2 is positive, we typically use the log of lambda 2 as a data, and we expand the log of lambda 2 with the PCE. And then, as I said, we use standard PCE, sparse PCE method called hybrid logs. Once we do this, so it works, I'll show you results, but we realize that basically we lose, we do this in two steps. So we lose somehow the coherence or possible correlation of the different samples for different x's. So the idea next was, could we do this in one step, really fit in one step from all the data, the coefficients of this polynomial representation, instead of first fitting the lambda for each xi and then fitting a PCE for the lambdas. So the idea here is to try to build a surrogate on this global joint distribution. So again, here the joint distribution of x and y would be what we look for, this conditional one, multiplied by the distribution of the x's that we know in practice. And here we will represent as before this conditional distribution with the generalized lambda, which gives us a representation now for this joint distribution. Now, the true joint distribution is not necessarily of this format. We want to find the best format in this family, GLD with certain parameters, that is the closest to the true distribution. And one way to do this is try to find those A coefficients that would minimize the Kullback-Leibler divergence between the true unknown distribution that we know only from data and this representation. So when we developed a bit this this equation, it ends up that the optimal coefficients, PC expansion coefficients, minimize this expected value of this log PDF. So here, again, if we know, or if we fix a priori the PC expansion of each lambda, which we could do, I say, I don't know, I take polynomial of degree 2 for each lambda term, and then I have a number of coefficients A, then the only unknown is A, and then everything depends, is conditional on A, and when you put your data here, you can formulate basically a kind of like, so that's the last equation here below. So if you take all your data points, xi, and for all xi, for each of them, you have R values of y, you can put this into this equation. So estimate basically the expected value over x and y from the data by simply just taking the average here of the data. And in this equation now, although it may be complex, but the only unknown are the PC coefficients. So you use an optimizer and you get something out of this. Just to show you a bit how it works, here I consider a very simple model, which depends on a single x, and for a given x, I assume that y at this given x exactly a lambda distribution. So it's really cooked for the purpose. The evolution of the lambda parameters as a function of x is just taken here for the example. So if I were to use this model and to sample data from this, this would be in 2 steps. First, select x's, here typically 20 values, and for each x, then use replications with whatever seed, and then get those points. And now I want to feed a model. These equations here, so the lambda function as a function of x that I've taken as an example, I've plotted with the line. Now, if I take the blue points, forgetting about what is the truth, I take the blue points for each x, I fit the lambda distribution and I get the 4 values, so that will be the circles. So you see that the lambda one is quite good, there is not so much problem, but when you go for, let's say, other parameters, then you can be quite far away from the truth. And then I use these circles, these red circles, to fit PC expansions. So that's what I get here. Blue is now the PC expansion. Again, it somehow captures well, let's say, the dynamics here. So here it's cubic, here it's parabolic, here it's linear, but it's not quite exactly the truth. If we use this joint fitting that I described, that is really in 2 steps. First, find a basis and find what are the PC terms that are relevant, and then fit jointly the coefficients, then I get much better results. And almost here, that's very simple, one case almost. So I have to come back here. So this looks very nice, but here, why can we apply this? Because to formulate properly this optimization here in the equation at the bottom, we have decided for the PC base for each lambda. And how did we do this? We did this because we did some inference before, point by point, or xi by xi. Okay. Now, when you look at this exam, at this basically problem of joint fitting estimator that I've shown already, and when you estimate this by just an average over of realization of x and y, if you know which truncated PC expansion you use, basically you don't need replications. So you could, maybe it's clearer here, this equation here, here we solved it by averaging over all n points and all replications. But now if r equal 1 and n is big, this is exactly the same thing. So if you don't have replications, you would be able to use exactly the same thing. Not having replications, that leads to the graph to the right here, the plot to the right, compared to the plot to the left, where x's are given, and for given x, you repeat 40 times the evaluation. Here, for each x, you get a different seed, you get a different output, so you get somehow a more denser cloud. So that's what's written here. Now, in this approach without replications, and this is useful because for certain problems, you may get let's say pre-computed data where basically you have no control on the seeds, and in that case you have no guarantee that you are in the situation to the left. So if you are given this data that's been generated for many different x's, and for each of them a different seed, well, what can you do? So we can apply this kind of maximal likelihood inference, but this supposes that we know exactly which PC expansion we want to have, because here it's just a way to compute the coefficients given the truncated expansion. And now, if we don't have replications, we cannot use the trick we used before. So how to do this? You could fix a priori, say, as I said, you take just a linear or second order polynomial variation for the lambdas, and that's it. So it's a priori fixed, so it's kind of decision. But if you want to be problem independent and smarter, we should find a way to let's say, a priori pre-select a relevant basis for the problem. So what we do is the following. Let me start with the last one. We observe that in many problems, lambda 3 and lambda 4, although they may vary, the shape of the distribution may vary when you vary the x's, they vary not too much. So here we do really the basics. So either just the PC of degree 1 or 2, and usually it's more than enough. For the lambda 1 and lambda 2, this is different. And remember that lambda 1 and lambda 2 somehow for lambda distribution are related to the location, that is the mean value, and the scale, which is related to the variance. So what we do here as a trick to find, again, the proper expansion basis is that we try to surrogate the mean function and the log variance first. And once this, we take exactly those sparse bases for lambda 1 and lambda 2, because we know that there is kind of one-to-one relationship. So now the problem is simplified to how to find a sparse PC expansion that is good for the mean function and the log variance. For this, we can use something that is called the feasible generalized least square, which works as follows. So you start from your data, and from your data, basically you do pure regression. So least square standard approach, which gives you a first estimate of the mean function. So even if there are a lot of noise, you can get this. And then there is an iterative loop. From the current estimation of the mean function, you subtract the mean function from the data points, you get the residual. And from the residual, which are now centered around 0, you basically fit a variance function. So you take the log of the residual and you fit this again with this expansion in our case, but could be also kriging, so as to get an estimate of this variance function. And then for this to be consistent with the data, we re-estimate the mean function now with weighted least square, taking into account this variance. Because if you look at my data points, typically here it's a heteroscedastic problem. So first we fit a mean, ignoring the heteroscedasticity, then we subtract the mean and get the residual. We kind of fit the variance, and then we iterate by refitting the thing with weighted least square. So this is illustrated with exactly those data points. This would be step 0, 1, where you have this mean function. You subtract the points and you get here the log of the residual, and you fit something. And then in the second step, already you see there is almost no change. So the change is just around my mouse here, you see. This is the step 0, and this is the step where I already have a weighted least square. So if you repeat this after just a few iterations, it's completely stable. It's very, very robust approach. And now we have, let's say, a PC expansion of the mean and variance. Maybe this is already good. All the people that use basically this Gaussian processes approach, they do nothing more than that. They just try to fit a surrogate to the mean and the log variance. So already we have this, but we go a step further. We use from this result just the sparse basis that is relevant for this mean and log variance function. And now this will be our basis for the lambdas, and we fit then the lambda with the maximum length. Okay, so I think I should go to the examples now. I have these three examples related to the three fields I mentioned in the motivation in the beginning. Here we have to talk about validation for a second, because as I said, when you talk about surrogate models, classical ones, well, usually it's very clear. You consider the mean square error or the maximum absolute error. These are the two standard values, and either you have a validation set or you do some kind of cross validation and you compute these indicators and everybody agrees on what it means. Here we have to compare distributions. So for a given x, I have to compare the true distribution y of x and my surrogate distribution. So we tested many things, and in the end, we ended up with the so-called Wasserstein distance, which is basically a distance between two distributions. That is the L2 norm between the quantile functions, as you can see here. So this is the two Wasserstein distance. Why we do this? One reason is that in our surrogate, basically, QY here is exactly this lambda expression. So here we have something analytical, but that's not the main reason. The main reason is that if we use some distances between PDFs or CDFs, in fact, it becomes tricky when the true Y and the surrogate do not have the same support. You end up with many critical numerical problems. So in the end, using some distance on the quantile function is better. And of course, we want to have an average accuracy of this surrogate, not just for a particular x, but for all x's in the input space. So typically, we will average this over x and normalize this. First example is these simple equations I have shown here. This is nice because we have two parameters. We have some stochasticity from this DW here. And more than that, if you use so-called ethos calculus, you have an analytical solution. So here at each instant t, S of t, so the stock price, is log normal distributed with the parameters here that evolve with time. So everything is, the reference here is a fully analytical solution. So we take this, now we assume that the two parameters are not well known, they vary with within certain range. And we are interested in basically the random variable S for t equals 1. And these are the results. So as I said, the reference here is log normal distribution that is perfectly known from the analytical solution. This is plotted in black. This looks log normal, and you see that it's always log normal, but depending on the x's, the value of the two x parameters, it can be more or less peaky, more or less skewed. The GLAM solution, so generalized lambda model, is our approach, and you see that it mimics quite well the behavior for various values of x's, and it's typically better than the, let's say, state-of-the-art non-parametric approach to this problem, which is just the so-called kernel conditional distribution. So what I've shown in the beginning, you basically do some kind of kernel distribution of the full data x and y. You divide by the marginal x, and you get this. We can do a proper convergence study here. So now, not just look at a few points, because with plotting distribution, you can always get results as nice as you want. But here we now suppose that we vary the size of the x's. Here we don't have replications here. So it's really the when I say 1,000 points, it's really 1,000 points with just one seed for each point, or it could be 200 points with 5 seeds if you want. So it's really the total cost here. We choose this, and for each size here, as everything is based on an experimental design, typically LHS somehow, we repeat this independently. So we do statistical replications just to get not just one value, but a box plot of errors. And these are the different solutions. So here we have the non-parametric here, which is the orange one. We have our GLAM approach, and we have what is called in green and black. This would be the normal assumption. So if you assume that for this problem you have a normal distribution, as many Kriging-based approaches do, the best that we can get is the black line. And indeed, if you use one of these recent package here of Gaussian process for this purpose, you see that this is the best error you can get. Why? But because of course the true distribution is not normal; it's a log normal in that case. So of course, we also, with our lambda distribution, we don't exactly have the log normal, but as we have the 4 parameters, we can get so close to the true log normal that it's much better. The SER model here, so again, it's a very, very simple version of it, just to showcase how it can work. We suppose here that we have a total population that is fixed, and just people change from susceptible to infected to recovered. Nobody dies, and once you recover, once you're infected, you recover after some time. And so the parameters of the transition from each of the states are the parameters, and also the initial population here of susceptible and infected. And now we have the output is the total number of infected people. So at the end of this outbreak, this will end, because here, well, nobody dies, and at some point everybody that can be infected recovers, so there is a stop. And the question is, out of or upon the initial infected individuals, how many individuals were infected? So we get a distribution here, and depending again on the parameters, you see that, well, this distribution can be more or less skewed. The mean value can vary from 100 to maybe 450, so it varies quite much. And here we get a reference just by running a brute force Monte Carlo and get an histogram for those validation points, and you see that again the GLAM gives very good results. We could do again a convergence study where again our approach is better than the standard non-parametric approach. And for, let's say, reasonable amount of points here, the optimal, or what we call oracle Gaussian solution, would be better, just because basically in that case the solution, this distribution, are very close to being Gaussian in most for most values of x's. So of course, if you assume Gaussian, you put a big constraint, and with less data you are able to fit a model. But after some point we can get the same accuracy. Finally, the wind turbine. I hope I have a few minutes more. Yes. So here, remember the plot at the beginning. We have typically 5 macroscopic parameters that define the wind conditions. And then for a realization of those 5 parameters, we can have many wind fields that are generated, and then that generate certain forces in the wind turbine. So here we have, on the one hand, and we have a special, let's say, fancy joint distribution of the mean speed, the turbulence, and the shear exponent, because that comes from real data. So we are basically sampling in uniformly within these curves here. We have here 485 training points. We have replications, that will be our training set. And then the test points will be independent points in this input parameter space. And we do 500 replications, because for these test points, we want to really have a quite accurate distribution to have a comparison. And these are, again, the results. So if we compare, we can have, again, the global accuracy, which is about 1% in our Wasserstein distance. And you see for, again, selected points here in the test set, not the points in the training set. Basically, the histograms from the 500 replications and the predictions from our GLAM model. Again, it's not perfect, but it's really quite good. In that case, which is really an industrial problem that we will work on more and more, it's nice to have a prediction of the distribution, but in the end, that's not, I mean, it's fun, but that's not really the main interest. The main interest would be really to have the mean standard deviation and typically 95 or even 90% quantiles. And so what you see here is that if we compare from the data sets the reference mean value and what we get from the lambda distribution, and the same for the variance and for the quantiles, it's quite good. So in a sense, even if you're interested in some upper quantile, it's a good idea to use the full data to fit the full distributions, let's say, conditional to the x's, and then post-process this lambda distribution, which is analytical, to get the quantile of interest, and you get very good results. So this will lead me to the conclusion. I think I'll be really just in time. I'm sure that you are convinced already that these stochastic simulators are very useful in many fields of applied sciences. We need, again, general purpose emulators because we tend to build more and more accurate simulators, and then as soon as we want to vary parameters, it becomes a computational burden. Here we introduce this so-called generalized lambda models, combining lambda distributions and polynomial Gauss expansions. This model is very versatile. So if you can use replication, so if you can yourself generate your data, you can generate with replications and you can use it. If you don't have replications, you can still use it. And the question is, with a certain number of points, is it better or not to get replications? And in fact, for most of the examples, replications do not bring anything. So you get overall a better surrogate model of the full machinery when you generate data points with different random fields. All this is based on tools that we have in UQLab. So what is UQLab? This is our uncertainty quantification software that we developed now for a few years. We have more than 3,700 users all around the world from 92 countries. Recently, the last one was Nepal. And this is MATLAB based, but our last developments is basically a cloud version of this, which is usable with Python language. So if you're interested, this is online just for 1 week or two. And if you're familiar with Python environments and you want to compare existing UQ packages in Python with UQLab, now you can do this fully with Python syntax. So just go to this link, register, and you will get it. We have also this UQ World community website where, well, people ask questions about UQ in general, UQ problems, how to solve this and that. Sometimes UQLab questions, but for sure not only related to UQLab. And we also post whatever information about conferences, summer schools, anything that is relevant for the UQ community. And with this, I'm done, and I thank you very much for your attention.
Thank you, Bruno. It was a very nice talk. If there are any questions, I guess you can just open up your mic and ask, or raise your hand. If not, in the meantime, maybe about this not using replications. You might have answered this, but does N need to be a lot larger if you don't use applications? It seems almost counterintuitive. Or,
yeah, that's the point. I mean, it's somehow so counterintuitive that we have all kinds of trouble to get this research published because the reviewers and mostly the editor of the journal is not convinced that you can do anything without replications. And still with our, I mean, we computed tons of stuff to show that still, well, we can do computation, and basically for a total same cost, it's often more relevant to not have replications. So that's it. So my intuition is that if you remember, maybe I can share the picture. That was showing the difference between the two different let's say types of runs. you can somehow think that here, well, you cover, let's say, a space filling in the X space, and then you have a tensor product with fixed values of omega in the other dimension. Whereas here it's kind of space filling in both X and omega, so you somehow have a more space filling in the full product space, and somehow you get more information. That's my interpretation, but
so it would be really nice, because we just did a big UQ campaign using a molecular dynamics code with replications. I think we used 25 replications, and we burn about 2 million core hours doing this campaign. So if you cut that by a factor of 20, that would be very nice.
Yeah, well, I mean, it's not so much, for the example we had, if we take, let's say, in total 1,000 or 2,000 points, we saw a better or smaller overall error when we don't use replications. But this may not be, or maybe may not hold for all problems, but that's what we observed on these simple problems. Yeah.
That's an interesting approach. Yeah. I think Dan has a question.
Yeah, that's right. So thanks for this very, very nice talk. So my question is about the generalized lambda distribution that you showed, and also the examples that you showed. This was all about situations where the simulator output or the quantity of interest is a scalar quantity. So I'm curious, are there possibilities, do you know of possibilities to generalize these to cases where the simulator output is multivariate and correlated?
Yeah, we did not try. So we did not, with this kind of approach, we did not try, because what you surrogate is really the distribution, not the output random variable. In the sense of when you do classical polynomial chaos expansion, what we get in the end is a polynomial expansion. So we claim somehow it's a surrogate of the function. So you replace the function by a function, but the theory behind is basically that you expand the output random variable in a certain basis. So it's equivalent in a sense, but you have two, if you want, two interpretations. On the one side, it's pure functional analysis, approximation. On the other side, it's a representation of a random variable. Here with the lambda distribution, we represent, let's say, the PDF or CDF or inverse CDF to be accurate. And so here I see difficult to generalize to multivariate, because then you would need a, well, okay, you would need a multivariate lambda distribution and some kind of copula. Why not? But I see the complexity possibly, well, exploding easily. Now we have another approach, which I did not present today, which is, I think there is an equation relevant to this, which is exactly this one. So here we want to represent the random variable here as a function of some latent random variable. So here it's again kind of representation of a variable, so that you have kind of equality in distribution. And here we basically, again, use for n tilde a PCE that depends on the input, and some ad hoc introduced additional variable that embed the stochasticity in a lumped way, in a sense. Okay, so this is recent. The reason it gives even better results on the exact same example. We can get better accuracy. And the nice thing is that if you were to have output distribution that are bimodal, there's no way with the lambda to capture this, but you could do this with this. And is then again a pure, I mean, there is some trick, but it's very close to the standard tools for PC expansion. Then there is no problem to multivariate, because for multivariate PC expansion, either you have the same basis, so then it's very easy to project the coefficients. If you have many but very much correlated output. You have this idea of principal component analysis that you can couple with PC. So all this is well known for the deterministic case. And I see a way to, if we manage to extend properly to the stochastic PC, then this will be the way, in my opinion.
Okay, so but that would not be, so that's a different approach that does not attempt to parameterize the output distribution.
No. Yeah.
Okay.
Because already here, if you have a single output, well, a single output distribution function of X, you have 4 lambda parameters, and well, depends on the dimensionality, but typically for each lambda, you may have 50 coefficients. So you have in total a problem parameterized with a high number of coefficients. So now if you multiply by the dimension of the output, very easily you get thousands of coefficients. And the way with a kind of maximum likelihood, I mean, it's tricky to optimize in such a high dimension. So then maybe we should go to other solvers. I don't know, maybe neural networks or something.
Okay, thanks.
Okay.
Benjamin and Richard, either one, maybe. Benjamin first.
I had a very similar question to Dan, but I can follow up a bit maybe. So if you express the PDF or what the inverse CDF in terms of the 4-parameter lambda distribution, in the end you still commit an error, right? Because you restrict yourself to 4 parameters, let's say compared to the exact CDF. And so does it appear in your convergence plots at some point if you keep on adding points? Because it seems it keeps on converging, but don't you reach the limit?
On this example, so all these examples are examples with unimodal outputs, like close to Gaussian, or if not Gaussian, well, nicely skewed to the left, to the right, with possibly the skewness varying with X, that's okay. And in this case, these lambda distributions are so flexible that we should go very, very far away to see the plateau. There will be one, but yeah. But if you give, I mean, we have cooked problems, simple ones, where on purpose it's bimodal. Very easily you see that you don't get convergent because
And would it make sense to make the generalized lambda model so generalized that the number of coefficients is can be changed, can be arbitrary?
No, already I mean, for this purpose, we wanted to develop a slightly different version from the standard, what is called standard generalized lambda. But you have to check consistency. So here with this kind of construction, it's clear that well, this quantile or inverse CDF is monotonic, for instance, and so on. If you add more complex expression, then you have to ensure that it's an inverse CDF. And I'm not sure it's easy to do so.
Okay, thanks a lot.
Yeah.
Richard?
Yeah, hi. Thanks for the talk. I had a question about the correlation structure. So maybe this goes also to the replication question. So if you're able to work without replications, you must be, I suppose, assuming some correlation in the X variable. And I was kind of wondering from your method where how this correlation structure is defined and where it comes from.
So let me go to, I don't know. Yeah, it's not, there is no really, if you want the 4 different lambdas are expanded onto the same, or not the same basis exactly, but let's say the same construction. At least there is a common basis if you want, if you put some zeros somewhere. So intrinsically then, if you would ask me, okay, what is the correlation between lambda 1 and lambda 2, that is something that is automatically taken into account. But the thing is that we don't use something like I don't know, the cross correlation of y of x1 and y of x2. That is not something that directly gets into the problem. So we don't compute this. It's just another representation. So if we were to use Gaussian processes, probably some kind of correlation structures naturally enter the game. But here it's not the case. It's really for each given x, we want to represent the marginal. And what is interesting is that indeed we don't get as an output. I cannot tell you what is the correlation of y of x1 and y of x2. This is not represented, and then you cannot compute out of the model.
So when you're sampling from your surrogates, for example, you can't generate smooth functions in terms of x. You're really sampling statistics.
Well, you can because you can get smooth samples which I mean, somehow in the end, let me come back to this equation. So sometimes in the end, you get here exactly this shape for the inverse CDF, but now all the lambdas depend on the x. So for each x, you have different values. So if you, for instance, ask me what is the 95% quantile of all this distribution over x, I just use here u equal 95, and then I have a fully analytical expression of the 95% quantile as a function of x. Yeah, it's cumbersome, but it's fully
right.
So in this sense, it's
your quantiles are smooth, but there is no correlation.
No, there's no correlation.
Maybe that's something like the issue with the journal editor you said had with the replication issue, because normally you would have to assume some correlation between neighboring x for the information of the value of the response at 1x to be relevant for the value at the neighboring x.
And we don't do this, so that's
and you
why
don't do that, but you do have some
smooth
structure in terms of quantiles. So that's then serves as a replacement for this correlation structure in that case.
Exactly. So it's a it's a different source of connection, but it's not the standard correlation between points.
I guess it's related to some notion of continuity of the way the PDF changes as x changes, right?
Exactly.
That assumption must be there.
But that brings it's exactly something like I mean, that's nothing to do, but if you're familiar with system dynamics where people use the Fokker-Planck types of equations, you have evolutionary equations of the PDF, but you have nothing about the correlation in the basic equations. It's really a PDF of one quantity follows certain probability conservation, let's say, and then you have the dynamics of this. But if you have two different quantities, this does not give you anything about the correlation between these quantities. So in a sense, that's the weakness, if you want. But the point is really, if you look for the distribution and then typically quantiles or moments out of this distribution, point by point, then you get something that covers everything. Okay.
Yeah. Is there any last question, perhaps? I might have one small question. You said about a Python version of UQLab on the cloud.
Mm-hmm.
So is there some coupling to HPC machines there, or you can just run it on the cloud with very...
Well, let's say that the reasons behind is that, well, we chose many years ago to develop this in MATLAB for good reasons, not Python. We are still very okay with this, but indeed, more and more these kind of methods are closer to techniques used in machine learning, or let's say the two fields are getting closer. And Python is probably, the king for all machine learning toolboxes. So many people would like to do the same with Python, but we have close to 100,000 lines of code, so we don't want to translate it into MATLAB, into Python, and then maybe in 5 years into Julia or into R, a fancy new thing. So what we did is we have, let's say, standalone version of all this that is compiled, the MATLAB version compiled. And then this could be indeed distributed somehow. Why not? But then again, you have, well, all kinds of local fancy platforms, fancy operating systems, and so on. So you never know what you get. So a solution to this is to do this once and for all in a given environment, and this is running on cloud instances with containers and so on. And then basically the software, you just send requests to this server. So it's really software as a service. And the way to send requests is basically, well, to say, for instance, I don't know, define a probabilities model with this and that marginal, sample these things with Monte Carlo, or build a PC expansion with this and that data. Now the server knows this under a certain format, and the Python package is just the binding. So it's just a Python syntax that allows you to somehow send the nice request, and it's a few hundred of line codes. So it's very small, and if we tomorrow want to do the same with R, probably again it's a few hundred lines of code, and it's very limited. And then people have exactly the same results as they would have with the MATLAB version, because it's not libraries, different language. It's just the same compiled MATLAB code.
Maybe also good to add that you now have the HPC support in the MATLAB version.
So that's different. So that's the
I understand that's different, but still not everyone is aware maybe of the recent version.
So this is something that from the beginning it was designed for this, but for a long time we had like just a private version and not very powerful. And now in the last release, indeed 2-3 months ago, we have this HPC module where basically you can almost transparently, if you are, you know how to connect to your distant powerful machine, there is almost nothing to change. You define what is called a dispatcher with, again, like how do you call this, configuration file. And then that's once and for all. And then anything you have developed locally with your small laptop or machine, once you have defined this dispatcher, it will just launch completely transparently all your simulation there, and now in an asynchronous way. So basically, then you can disconnect your MATLAB, and then when you reconnect to the server, it will send you back the results or give you the status. And so it's quite powerful. It's meant again for people not experts. If you're an expert in parallel computing and MPI and so on, already you could do all this by yourself. But the goal of this module, exactly as the UQ link we had to couple third-party software, is really for non-experts to do this in a kind of easy way.
Okay.
Yeah. Just a very brief question. So the material you talked about today, is that now also part of UQ Lab, or you mentioned it's sort of?
No.
You
not yet, because
using elements from UQ Lab, but the
it's not in the version. Somehow we have this in our internal development version. It's not in the public release, documented and so on version yet. It will be, but it's also, the PhD student was rather productive, various approaches, and in the end, probably in UQ Lab will be what we consider the most efficient, and not necessarily everything. So, and this is probably, next year, because it's now close to the end. So towards the end, it will be done with all the publications and everything, and it will put all together this. So it's not for next 2 weeks, but it will be someday. Yeah.
Okay, I'm looking forward to that. Sure. Thank you.
Yeah. I have a question, by the way, which is in common maybe. So I saw that you have really interesting big models and obviously a lot of data, as you said, maybe millions of hours of simulations. So is there any way that we could use your pre-run data or some example just to somehow benchmark or make more robust the thing, see it work, if it works or not for real problems. Is there a way for, let's say, collaborating in this respect? Or is it, let's say, private collaborations you have already and the data is not public and, well, full stop?
No, as far as I'm concerned, we can just share the data. Although the source code and stuff we develop is also open source, so
also available.
Okay.
Yeah, I see no reason why the data should be any different. I have, for instance, quite a lot of results for this COVID sim model. That is this.
Yeah, this is because I read this paper where you actually have a very complex COVID sim model with many parameters, so not stochastic. In the end, I guess you just take the non-stochastic part, but in rather high dimensions, and typically all these sparse PC techniques that we have, I mean, for other problems, it's much better or much more efficient, let's say, than sparse grids and these things when you are in really high dimensions. So that would be also something, if you're interested, we could try to have a look.
Yeah, sure. I can share the data if you want.
Yeah, so well,
I guess you'd also need a simulator, or no?
Well, that's already open source as well.
Yeah,
but the thing is that if we have to get into the simulator, although it's open, this is well, takes some time. It's difficult. We will not generate the same data, and if we get very different results or not so consistent, well, we never know if it comes from us, from the different data, from whatever. So that's why, I mean, if there is a point of comparison, and if it's of interest to you because of, I mean, future projects, of course, this is a possibility. But,
maybe it would be maybe the data that we have for the Veersim model, right? So we did another study also on an epidemiological model.
Yeah, that's the one I sent
really
you,
retained the stochasticity, right? So Federica Gugolo, I can see is listening in. Has done that a lot of the work there. I think that could be.
Yes, the data is on the server of the CWI computer, so we can easily share it with whoever we want. Also, the Veersim model itself is open source. Is everything open source, so we can share.
Okay, well, let's keep in touch and see as a follow-up if there is something reasonable and meaningful for you and for us.
Yeah, okay. I guess we can be in touch on this, I guess, offline. See what's possible.
All right.
Thanks a lot again.
Well, thank you very much for the invitation and the discussion.
Yeah, many thanks.
Yeah. And well, have a nice day.
Thank you.
Bye-bye. Thank you. Bye-bye.
Bye.
Bye-bye.
Thank you. Bye-bye.
Hey guys.
Hi. Still recording, Wouter?
I think Wouter has already gone. Oh well.
Oh no, not fully. It's probably his computer is now trying to digest this recording, I guess.
Exactly. Okay. I should move on.
All right. Yeah, I'm also tuning out.
See you. I don't know when it is that CWI is going to be opening up again properly, but let me know when it does. And it's probably going to be later this year, hopefully. But yeah,
I'm hoping to after the summer, and then it'll be great if you can.
I'm quite missing the connection. This is really nice, but it's it's not quite the same. There's lots of fluid dynamicists around here, but not many mathematicians.
You're very welcome to come to Amsterdam again, obviously. Once I'm not sure when we can open up again. Hopefully after the summer.
Yeah, hopefully. Anyway.
Yeah.
Good.
Okay.
Have a nice evening.
You too. See you. Bye-bye.